Ladies and gentlemen of Algebra 2 Honors, welcome. Good afternoon. Hope everybody's having a good day. We're going to resume where we left off yesterday, which was on completing the square. And after having done yesterday numbers 7 and 8, we looked ahead briefly at 9 and 10 and noticed that there was what in 9 and 10 compared with 7 and 8?
A number in front of x squared.
The number in front of x squared, which is going to increase slightly the complication of these things. And so what I propose to do is to work out number 9, have you pay attention to that, and then we're going to start calling on people for number 10, all right? So I'm just going to start out by rewriting this as f of x, and factor out a 3, and then open parentheses. So 3 times what equals 3x squared? Well, x squared, right? So that makes sense. And then we have to look at this 24x. What times 3 is going to equal 24x? 8x. Is that J? Is that you, Jay?
Yes, sir.
Yeah, Jay says 8x. Is that right? Is he right about that? Yeah. And then we're going to add something we haven't figured out yet, and then subtract over here, and finally add the 53. And so how do we determine what goes in here to complete our square?
Divide 8 by 2.
Divide 8 by 2. Okay, let me go ahead and do that. Okay, so we take that middle coefficient, divide by 2, and get 4. And what do we do with this 4? 4 squared equals 16. And so 16 will go right in here. Okay, and what goes out here?
Yes.
16, like this. Is that right? I want you to look at that and think a little more deeply.
Oh, no, got the Tom's I don't know.
What do you got here? What is this going to be instead of 16? Negative 16. 48. Is that you, Peyton? That was Ben? Ben says hesitatingly. No, but it is 48. Why do we subtract 48 here?
Why?
Because of that 3 in front of
Yeah, so it looks like you've added 16, but you've really added 48. Because we have to remember that this 3 is multiplied by the 18. So this is one step where people make mistakes on completing the square. So let's just go ahead on this. So we got 3 times. What is our completed square on this thing? X what?
Plus, like x squared for you get rid of
X plus 4 squared. And what goes outside here? Negative 48 plus 53 plus 5. And then what you'll do is you'll test to see if this form here, standard form, is equivalent with vertex form. I think if you'll do that, you'll see that they're equivalent. Any questions on this one? All right, what I want you to do is work out number 10, and then I'm going to choose somebody with our name generator. We have Peyton, who is back there taking advantage of our literary initiative, book shelving. All right, I'm going to have someone help me with this. And I'm going to spin the wheel here. Let me go ahead and shuffle this a little bit. See, okay, now we're going to spin. Looks like it's going to be Jay again. All right, Jay. All right, Jay's going to help us out with number 10. I think he did it yesterday, right? So go ahead, Jay.
Fx equals 9 and eventually x squared plus 2x plus 1 parentheses minus 9 minus 3. And then we got f of x equals 9 parentheses x plus 2 parentheses squared minus 12.
Is that what you said there, Jay? All right. I said x plus 2, but that's if you said that.
Oh yeah, no, I said x plus 2.
Well, it's x plus 1, right? Right, okay. Any questions on that? Did you test for equivalency on that? I hope.
You got this.
All right, Jay. Now we come to problem 11, which is different than the others in a few respects. Does number 11 look harder than number 7 through 10?
Yes.
Yeah, because we got to read.
What makes it harder?
Words.
Words, word being a word problem. What else? Fractions. Fractions. And another thing that someone else mentioned is the numbers are pretty large too, or pretty small, the way, depending on how you look at it, right? So, but if we apply the principles, we'll be able to, if we can manage to learn how to swim in a pool where the water's 3 feet deep, we certainly have the skill to swim in deeper waters, don't we? And coincidentally, we're swimming underneath the Golden Gate Bridge. By the way, I have a cousin, Paul Giroux, who's an expert on the Golden Gate Bridge. He gives lectures. What is that?
He jumped off the bridge?
No, he did not. My cousin Paul is still living.
You can still live.
You can, but it's pretty rare. Most people who jump off that bridge. Do not live beyond smashing flat on.
It's so bad.
Okay, but what we have is it says instructions, complete the square to write the function in vertex form. So we're just going to use the same principles we used earlier that Jay helped us out with on problem 10. And so we're going to have Jay or others help us out with what's going on here. So the first thing we're going to do to complete the square, we're going to take this 1/9,000ths out here, right? And then inside we have x squared, and what's going to go here next? Okay, we're going to take -7/15, and what do we have to multiply by to account for this 1/9,000? We got to multiply by 9,000. So we're going to have, that's going to be x, and then we're going to have plus some number here, and then minus some number here, and then finally we're going to have plus 500. And by the way, I didn't tell you this, is we're considering this tower, this left tower of the Golden Gate Bridge, as where the X and Y axes meet at the origin. And so we're talking about the shape, we're talking about the curve of the span of the bridge right here. That's what this equation or function finds for us. Okay? So how do we determine what number goes in here?
By 2.
Multiply by 2. Well, we're going to take the negative we're going to divide by 2. Same thing we've always done, right? So we're going to take negative, which is going to be -7 times 9,000 over 30. So -9 times did I get this wrong here? -7 times 9,000. That's like it wrong. -7 times 9,000 divided by 30. 2,100. -2,100. And what do you do with this 2,100? Square it. So we get 4,410,000. So here we are, 4,410,000. And what do we put out here? What goes outside here? Well, it's going to be this divided by 9,000. So let's go ahead and divide that by 9,000, see what we get. I hope this works out. 490. So 490. So now we have this h of x is equal to 1/9000th times x, x what?
It'd be plus 2100 or minus.
Minus 2100, right? Squared, and what do we have left here on the outside?
10.
Plus 10. So next question, B, what is the vertex? Vertex is what? What is a vertex?
Is it 2100 negative 10?
$2,110, right? And so that's going to be this point right here, 2,100, comma 10. And what does that represent? The low point in this cable, right?
Yeah.
Of the cable span. I'll put cable span. The left and right towers have the same height. What is the distance in feet between them?
4200.
Okay, distance equals 4,200 feet. And how did you determine that?
Because 2100 was right in the middle, so I just multiplied by 10.
Yeah, so it says 2,100 is over here, so you multiply by 2. So I'll just say multiply 2,100 by 2. So that's it. Okay, any further questions on that one? Okay, we're going to have a friendly volunteer pick up those papers. I don't know who's a friendly volunteer today. Connor.
Yeah.
You missed the spot.
I missed a spot here. Yeah, I did.
Up there on the bridge.
On the bridge, I missed a spot too. Oh, right here, okay. Well, what happens if I miss a spot sometimes and I don't save it, it'll be gone anyway. Now we're going to work on, we're going to start on some exercises, other exercises.
Like jumping jacks? Like jumping jacks?
Yeah, that's right, exercise like jumping jacks. Jay's mentioning exercise like jumping jacks, but actually I could use some jumping jacks. You know why? Because I'm tired. I need to have some energy infusion. I don't know about you. Is anybody else tired like me?
Yes. Hey, tell you what, back up the papers.
That's okay. I need to exercise now too.
Oh. That's what you said.
I need to have some exercise.
You didn't hear you. You say louder.
Today Addie was trying to trick me. She came the other way. So, but I caught you, didn't I? Yeah, I caught her. The wrong way. Well, Jay, I gotta hand it to you because in the afternoon, for you to have enough alertness to joke around, that tells me something. You ever get tired? It's like, doesn't your sense of humor kind of go? I just wanted to see. All right. Anyway, we're going to have at the beginning of this kind of a mini discussion on something called projectile motion. Does anybody know what projectile motion is?
The motion of a projectile.
The motion of a projectile, yeah. So I'm going to explain what it is. It's really a classic physics problem. Is anybody taking physics? Yeah, you're taking physics? Did you do projectile motion in physics yet? Not yet. We probably get to it. Okay, what it is it has to do with position due to the effect of gravity, essentially. So this shaved off football is a projectile whose elevation can be tracked or calculated versus time with a projectile motion equation. And you can see that when you toss something up, it initially will go up pretty fast, but then at the top, what happens? It slows down and before start coming down faster again. Yes, my sister-in-law made this for a Super Bowl party years ago. It was back when there was a scandal with the New England Patriots.
Deflating football.
Deflating football, yeah. Tom Brady allegedly was deflating football to make it easier to throw or whatever. Yeah, so there was that, and they also had the New England Patriots had other scandals besides that too. I'm trying to get every advantage. Sometimes, pardon me?
You come to the game on Friday?
I hope to, it's gonna be here, right? I hope to be there too. What is your number? 12. Okay. Defensive back field? Yeah, okay.
Sometimes I'll play receiver.
All receiver too? Okay, good. So anyway, what we have is projectile motion has some classic equations, and we're gonna go over that briefly. And so I'm going to put down what the equations are, and we're going to explain what these things are. We're going to have h of t, and height as a function of time is equal to negative 16 t squared plus v sub 0 t. So that's a little subscript 0 plus h sub 0. And we'll talk about what these are. V sub 0 is equal to what? Well, it's the initial velocity. What is going to be h sub 0?
Initial height.
H sub 0, Jay says, is initial height or initial elevation. We'll call it height because that fits better with h, right? Initial height. And so this is just a standard formula, and this is one for the units in feet. And I'm going to put down another equation that's very similar to that, which is h of t is equal to negative 4.9 t squared plus v sub 0 t plus h sub 0. So what is this formula or equation here? What is this equation going to be here? Any ideas? No. Close to yards. Units in meters. Now, is the gravitational pull the same are constant everywhere on Earth? No, it is not. Why is the gravitational pull not the same everywhere on Earth? What would you say, Marcus? Elevation, right? Does elevation make a difference? Yeah. If you have the highest point on Earth is Mount Everest, 29,002 feet or whatever it is, and the lowest elevation is the Dead Sea, which is like in Israel, which is like 1,400 feet or something like that below sea level. And so where is the gravitational pull going to be greater? At low elevation of the Dead Sea or high elevation of Mount Everest? It'll be low elevation because gravity will vary with inversely with the square, really. So that's the relationship of gravity. You'll cover that in physics soon. And so there's that, and there's also what else besides elevation? That's a good one, Marcus. What else is there? A couple more things other classes have come up with today. Okay, there's gravity from the sun and the moon, right? That cause the tides. So that will vary what happens on the Earth. And is the mass of the Earth the same shape and density all throughout? No, it's not. Density varies. The shape is not a perfect sphere. So there are irregularities. But fortunately, even with those irregularities, these formulas still hold true to a low degree of tolerance, no matter where we are on Earth. And to me, it's because, it seems to be, because relatively speaking, if you take the radius of the Earth, which is something like 4,000 miles, if you take the difference in elevation between, say, the Dead Sea and Mount Everest, that's going to be only 5 or 6 miles difference out of 4,000. And so it's not going to be that great of a difference when it comes down to that. So these hold pretty true. So we could use these just about everywhere. And we're going to use these with most of these problems. I don't know if these all are in meters, but I'm going to now erase these now. Any questions on these formulas? Okay, we look at problem 12. We have a technician launching an aerial firework from a 200-foot tower. Firework's upward velocity at launch will be 176 feet per second. And then we have professional fireworks are usually timed to explode as they reach their highest point. And we're asked to, how long does it take the firework to reach the maximum height? What is that height? And so forth. Now, it doesn't give you instructions as specifically as we did here. In problem 11, it said complete the square. What do you think might help us to do in problem 12? Complete the square. So we're going to go about that. So for that, I'm going to write, first of all, an equation in standard form, which is h of t, and we are in feet. So what is this going to be? Negative 16t squared plus, what is our initial velocity? 176 t, and what is our initial height? Plus 200. So this is what we're going to start out with. And so now rewriting this, trying to rewrite this in vertex form, we go ahead and take out what first? Negative 16 times what goes inside parentheses? T squared. And what's going to go here? 11, negative or positive 11? Negative 11t. And how'd you get negative 11t?
Because it's
So you're saying negative 16, if we multiply by negative 11, that's how we can get our 176, okay? So factoring out the negative 16 out of 176, so did you divide by negative 16, is that how you did it? Yes, if we divide this 176 by negative 16, we have what we need here. And then we're going to add something here, and then we're going to subtract something over here, or we might have to add it depending on what we have here. Plus, we have the 200 left over here, right? So what number goes in here?
I don't know. Like, 8. I don't know.
Because don't you
I
just
can't
divide by
remember
2?
that.
Okay.
30.25.
Yeah, so let's take, so Bryce says this, right? And so if we take this, we get negative 5.5. Is that going to be an important number for us?
Yeah.
Yeah, it is. And what do we do with that negative 5.5? Negative 5.5 squared. What did you get, Gabby, for that? You said it's something here. We say 30. 30.25. So we're going to add 30.25 here. And what do we subtract out here?
30.25 times negative 16.
So 30.25 times negative 16,
484.
484, but we're going to have to add that, right? So plus 484. Does that make sense? So now can we write our completed square here? Yeah, negative 16. And we're going to have t. What is it going to be?
Maybe 5.5.
Minus 5.5 squared plus 684. And so now we have, how long does it take the firework to reach its maximum height? So maximum height is reached at t equals how many seconds? 5.5 seconds. And what is the height? The height is, I'll call it maximum height, is 684 feet. Okay, off ground. Okay. And then the last thing we have here is part B. What is the average rate of change in the fireworks height? How do we find average rate of change? We have to look at A. Okay, average rate of change, average rate of change is equal to the formula I had here, f of B minus f of A over B minus A. And what this is, this is just a version of the slope formula. That's all that is. So what we're going to do at 0 to, the first half seconds, we'll have 0 to 0.5 seconds. Let's put 0 to 0.5 seconds. What we have is f of B, we don't know yet, but what's f of A? 0. What's the initial height? 200, right? So we can go to our calculator and we can find out at 0.5 seconds, 0.5 storage x, and just type that in. So we have negative 16t squared plus 176t plus 200, right? And so we're going to get 284. So we're going to get 284 minus 200 over in 0.5 seconds. So that's going to be how many feet per second?
Oh,
168 feet per second.
wow.
Okay? And next, we're going to have now 5.5 seconds before reaching after rising, we're going to have at between 5 seconds to 5.5 seconds. And so for that, we're going to have, now we know our maximum height is going to be 684 feet, right? So we're going to find out what this is. And what I'm going to do for this one is use the other equation. So I'm going to put 5 storage x. And now I'm going to use the vertex form, which is negative 16 times, we're going to have x minus 5.5, and we're going to square that and add to it, how many? 200. And we should get the same sort of thing we should have got, right? But that's not right. Times 684, it should have been 684, right? So I'm going to fix that. Negative 16. And we have x minus 5.5 squared plus 684. So we get 680. So we have 684 minus 680 divided by 0.5, and what's that going to be? What is that going to be? 8 feet per second. So we have, so those are our average rates of change. And what I want to do today is kind of leave it there, and we're going to just start on number 13. And what I'm going to do with number 13 is probably look at random name selection tomorrow and leave it at that.